So now that we've reviewed some of the background of matter and the categories that it can separate into, we're going to be looking at the pure substances category mostly. So let's take a look at the history behind the periodic table of elements. So what is the periodic table of elements? Some of you may remember it from grade 9, but essentially you can break it down. The word periodic means patterns or properties that are repeated regularly in a cycle. So a man named Dmitry Mendeleev created this periodic table in 1869 when there were only 63 known elements, and he noticed patterns in the ways that these elements behaved and arranged them by atomic mass. He left open spaces where he predicted the other elements would fill in, and these elements had not even been discovered. So here are some of Dmitry Mendeleev's first works of the periodic table of elements. And as you can see, many of the spaces were left open for the other elements to fill them in. So he predicted, according to atomic mass, that as the atomic mass number increased, there were other elements out there that he hadn't yet discovered. Elements on the periodic table are represented by symbols. And each symbol is an abbreviation for the element's name. Element symbols were created using either the first letter or the first two letters of the element name. The first letter is always capitalized and the second is always lowercase. Here's a couple examples. Hydrogen is represented by capital H, carbon is represented by capital C, and helium is represented by capital H, small, lowercase e, and lithium is represented by L, capital L, lowercase I. Other elemental symbols were created according to the Latin name of the element. For instance, copper, its Latin name is cuprum, and its elemental symbol is Cu. Lead's Latin name is plumbum, and its elemental symbol is Pb. Mercury's Latin name is hydrargyrum, and its elemental symbol is Hg. Potassium's Latin name is kalium, and its elemental symbol is K. Gold's Latin name is aurum, and its elemental symbol is Au. So as you can see, either the first letter or the first two letters are taken from the Latin term of some of the elements on the periodic table. So Dmitry Mendeleev arranged his periodic table according to atomic mass. Today, the periodic table is arranged in order of increasing atomic number, and it's still growing. So of the 118 elements that we know of, there could still be more out there. So the periodic table is arranged in order of increasing atomic number, and we can see the atomic number is represented in the left corner of every single box. So we've got 1, so hydrogen has 1 proton, helium has 2 protons, lithium has 3 protons, and beryllium has 4 protons, boron has 5 protons. So the atomic number is a representation of the number of protons. So there's a few different things that we need to know when we're looking at the periodic table of elements. The atomic number being one of them and what that stands for, and the atomic mass number being another one. And we need to know what that stands for. Let's look at the atomic number. Subatomic particles make up every single element. There are 3 main types of subatomic particles. If you can recall from grade 9, those 3 subatomic particles are the electron, the proton, and the neutron. We use the number of protons in an atom to determine what element it is. So for instance, the number of protons in hydrogen is 1, and we classify 1 proton as hydrogen. We classify 2 protons as helium. Looking at your periodic table, what do you classify 3 protons as? Lithium. Good. And what do you classify 5 protons as? 10 protons as? 25 protons? 92 protons? Take a look at your periodic table and see if you can fill in the rest of this chart. Pause the video here before I reveal the answers. Here are some of the answers to the number of protons. And the number of protons is also known as the atomic number. Now that we've looked at the atomic number, which we see in the left-hand corner of our periodic table's elemental boxes, let's take a look at the atomic mass. The atomic mass number is represented at the bottom, in this case, of the periodic table boxes. The atomic mass number normally is a decimal place, and it's a decimal place because the weight or the mass of protons and electrons and neutrons is 2 decimal places. So let's take a look. The atomic mass is the total mass of an atom. We can calculate the atomic mass by adding the number of protons with the number of neutrons, but we don't add the number of electrons because their mass is not quite significant. So if we take a look at the protons and the neutrons in comparison to the electrons' mass, we see that the proton-neutron mass is much larger in terms of mass units. So we've got negative 24 grams, times 10 to the negative 24 grams, and in this case we have times 10 to the negative 28 grams. So in scientific notation, if you're looking at that number line, your negative 24 is a larger number than your negative 28. So keep that in mind. The electrons have a very, very small mass, and it is essentially 0 atomic mass units. The electrons are the negative charged particle, the neutrons are neutrally charged particle, and the protons are a positively charged particle. Neutrons and protons are very, very large in comparison to the electrons. And if you think about the atomic mass, or the atom's structure, which we're going to look at later, you can kind of think of the sun being the neutron protons, and it has the largest mass. And then you can think of the electrons as planets orbiting the sun. The electrons are very, very small in comparison to the neutrons and the protons. And because the electrons weigh so little, they are the ones that orbit the nucleus. So they fly around the nucleus in a circular pattern. And the neutrons are inside the nucleus as well as the protons. When an atom is in a normal state, which means it has no net charge, it has the exact same number of electrons as it does protons. The charges cancel out each other and the atom becomes stable. So in these examples here, we have hydrogen. It has an atomic number of 1, which means the number of protons is 1, and the number of electrons is 1. When the number of protons and electrons is equal, the net charge is 0. Same with oxygen. Oxygen's atomic number is 8, number of protons is therefore 8, and the number of electrons is 8, so its net charge is 0. Pause the video here and see if you can finish the iron and carbon rows. The atomic number of iron is 26, so it has 26 protons, and you can determine the number of electrons by taking that atomic mass and subtracting it from the number of protons, and you should get your number of neutrons to be 0. Your net charge is then 0. Same with carbon. Now that we know a little bit about the atomic structure and what atomic mass and atomic number is and how to calculate them, let's put this into the Bohr-Rutherford diagram model, which we've learned in grade 9. So in the Bohr-Rutherford diagram, electrons orbit the nucleus and they may be transferred through ionic or covalent bonding. Here are some examples. In order to fill in these Bohr-Rutherford diagrams, let's take a look at this example. The protons and the neutrons are represented by red and yellow, and they're depicted in the center of the atom, or in the nucleus. The electrons, because they weigh so little, they're the ones that orbit around the nucleus. They fly around the nucleus in a circular pattern. So let's look at some examples. For hydrogen, it has 1 proton, and therefore it has 1 electron when it has no net charge. So that 1 electron gets thrown into the orbit. Helium has 2 protons. It has an atomic number of 2, and its net charge, when it's 0, it also has 2 electrons. And those 2 electrons orbit the nucleus. Now, the first orbit in Bohr-Rutherford diagrams can hold up to 2 electrons only. Only 2 electrons. So then what happens when we get into a second orbit? Let's take oxygen, for instance. Oxygen has 8 protons. It has an atomic number of 8. And when it's neutrally charged, or when it has no net charge, the number of electrons is also 8. So let's draw those electrons in around the nucleus. So if we've got oxygen's nucleus of 8 protons and 8 neutrons, let's take a look at the number of electrons. 2 will fill the first orbit. So there's 1, 2 electrons, 3, 4, 5, 6, 7, and 8 electrons. So now that we've fulfilled the number of electrons that oxygen needs when it has no net charge, this is its Bohr-Rutherford diagram. The second orbital, when we're filling Bohr-Rutherford diagram orbits, it can only hold up to 8 electrons. And for the time being, in grade 10, we're going to say that this third orbital can hold up to 8 electrons as well. So pause the video here, and I want you to determine what the Bohr-Rutherford diagram is for magnesium and for chlorine. Don't forget to follow the rules where the first orbit can only hold 2, the second orbit can hold 8, and for the time being, the third orbit can hold 8. So pause the video and give them a try. When you come back, let's go through the answers. So for magnesium, when you look at the periodic table, you can see that there are 12 protons because magnesium has an atomic number of 12. So then, if it's net neutrally charged, if it has a net charge of 0, then the number of electrons are going to be 12 as well. Let's start filling the Bohr-Rutherford diagram with 12 electrons. The first orbit will have 2. The second orbit should have its full 8. And the third orbit, we only have 2 more to place because we've got 1, 2, 3, 4, 5, 6, 7, and 8. So this third orbit should only hold 2, and that is magnesium's Bohr-Rutherford diagram. Chlorine has an atomic number of 17, so it has 17 protons, and when its net charge is 0, it has 17 electrons. So to fill that Bohr-Rutherford model, the first 2 orbits are going to be completely full, with 2, and the second orbit with 8, and the last orbit is going to have 7 electrons. In the next video, we're going to be learning about what those outermost electrons mean for certain elements, and we'll talk about some of those trends in the next video.